Welcome to the next module. In this module, we will be looking at Arctic amplification, local forcing and feedbacks. There are few questions which we are going to answer in this particular module. The first one is Arctic amplification. Is it a new event? Was it an anticipated event or an unknown event? Is it specific to few regions in the Arctic or to the entire Arctic? Is there any cause and effect between global warming and Arctic amplification? How do observe snow ice melting? Is it a qualitative measurement or a quantitative measurement? So these are some of the questions which we will be addressing in this particular module. Here is an image of the satellite observation and amplification emergence. So if you look at this image, here the Arctic amplification temperatures are given from -1, -0.5, 0, 0.5, 1 and 1.5. This degree centigrade difference is given in the y-axis, and in the x-axis it is the year-wise. From 1980 onwards, we are seeing till 2020. What is the observation per year increase in the Arctic? So this is what we are actually going to look here. The graph starts from 1978. So we can assume that 1978 as the 0 year, and we are going to see how the Arctic temperature had increased over a period of a couple of decades. So in the beginning it reduced. The blue line is actually the Arctic temperature anomalies. That means the variation in the Arctic temperature is given as the blue line, and the black line shows the northern hemisphere temperature anomalies, and the colored bars show the amplification. So how much is the amplification? So if you look at in the up to the year close to 2000, we are seeing the temperature was actually reducing. That means the blue line, if you see, that is mostly in the negative region. So overall, up to the year 2009, we see the Arctic temperature did not increase. So it was actually decreasing over several decades. But from 2000 onwards, there is a consistent increase. That means the persistent amplification started from 1999 onwards. So here we see the temperature gradually increases. So in the beginning it was up to 0.5 degree increase, but then it went up to 1 degree. In the year 2005 it was close to 0.7 degree, and then in 2010 it was close to 1 degree increase, and in fact in 2016 it was close to 1.5 degree increase. So if we consistently look from 1999 onwards, the temperature keeps on increasing. So this is what is the real observed data for the Arctic amplification. Now, how do we actually get the ice data or image? Because if we are going to see how much ice is retreating, or how much ice is disappearing, or how much ice is melting, so how do we know? We need to monitor that to figure it out. Like, how much ice was there previous year, and how much had disappeared in this year, and in the future how much is actually decreasing. So we do need to get the data to understand how the entire thing is changing. Let us look at how do we get the ice data or the image. The National Oceanic and Atmospheric Administration, the climate data record, or it is also called as Rutgers snow cover data set. This gives the snow cover maps at a 25 km to 25 km grid. And then there is MODIS spatial resolution, that is moderate resolution imaging spectroradiometer. This provides the data with a spatial resolution of 250 meters, 500 meters, 1000 meters and 5600 meters. Its accuracy basically depends on the time of the day, season, land cover and topography. When there is cloudy, then this kind of data what we are getting are going to be inconsistent. And visible infrared imaging radiometer suite, VIRIS. This data streams 500 meters, 1000 meters and 5600 meters resolutions. And there is also the European Space Agency's Globe Snow product. This has an intermediate resolution, that is up to 25 kilometers it is having a resolution. And the Copernicus Global Land Cover Service, this is the very recent one. This provides snow water equivalent for the northern hemisphere at 5 kilometer resolution. So all these data are basically based, many of them are based on the satellite images. So from the satellite images, we are actually going to look at how much is the thing that is keeps on changing, because these satellites will take images on a regular basis. So every day we can actually monitor how much is the change that is happening. And let us look at the genesis of Arctic amplification, because we have been asked, we know that the Arctic is getting heated up compared to the rest of the world, little bit higher. So that is what we have seen from the previous data, like from 1999 onwards, Arctic is getting warmer more than the global average. So what is the genesis of this particular Arctic amplification? So there are various factors which are involved in that. The first one is surface state transition caused by the sea ice retreat. So this is one of the cause. Then surface state transition caused by the snow cover retreat. Then surface atmospheric coupling effects, the Arctic energy budget, and the Arctic cloudiness effect. So these are all the various parameters which affect how the Arctic amplification is actually coming up. To fully understand the mechanism driving Arctic amplifications, it is essential to explore various surface state transitions and atmospheric interaction. The first one is the surface state transition caused by the sea ice retreat. So here is the image which we can actually see. There is an anomaly, because this is measured in different months over a period of 1980s to 2020. So this is over a 4-decade long data is given here. And here the yellow color area which covers, which clearly tells that from the year 2000 onwards, there is a marked difference in the sea ice retreat. In other words, the ice started reducing in the amount. So the global warming has been progressing without visible difference in its pace at low and high latitudes. Here in the Arctic, the sea ice thickness rapidly dropped by 1 meter, that is about 50%, manifesting a transition from multi-layer to seasonal ice cover. That means the ice are actually reducing from the multi-year ice. Multi-year ice are very thick compared to the seasonal ice, because we had earlier seen how the Arctic ice was actually melting. So that we have seen due to the albedo effect, and that is what we are also observing here in the Arctic amplification. There is a major transition of the multi-year ice that is occurring between from 2005 to 2010, and everybody agrees that the ice pattern and the overall extent and the trend are actually changing. Then where people are disagreeing is basically the ice concentration distribution in the marginal ice zone and the adjacent region. So this is where there is a little bit disagreement between various scientists, that whatever the data we are seeing may not be complete. From this graph, we can understand that the research shows there is a marked decrease in the multi-year ice, which has crucial implications for local ecosystems and climate feedback loops. Monthly variations in the Arctic climate trends indicate that the changes are not only rapid but also consistent across various measures, underscoring the seriousness of the issue. Let us look at the monthly variations in Arctic climate trends. So when the sea ice retreats, what actually happens is the sea surface temperature SST in the Arctic region begins to increase. So this actually happens in the month of August. So this is the temperature what we are actually seeing here. And the sea ice loss suggests that the rising influence of ocean fluxes. That means if more ice is melting, then that also affects the ocean flux. That means more fresh water will be entering the seawater. Sea waters are saline in nature. That means they are little bit denser compared to the fresh water. So the ocean fluxes are getting affected when there are more and more fresh water enters the Arctic Ocean. The thinning of the sea ice in winter leads to increase of 1 degree centigrade near surface warming per decade. So this is the observation what people had been seeing. In the Arctic amplification also we had seen that the temperature increase is maximum up to 1.5 degree. So this thinning of ice actually leads to an increase in the Arctic amplification factor by 37. So what is the relationship with thinning of ice and Arctic amplification? So basically when the ice thins, that means the albedo effect, that is the reflection of the solar sunlight by the ice, decreases over a period of time. So in other words, thinning of ice leads to melting of ice actually, and the melting of ice actually leads to more solar energy being absorbed by the sea water. So this is a positive feedback that is actually happening. So we can say when there is a thinning of ice, the temperature actually increases, and most of the times the near surface temperature just above the seawater also increases. And this increase in the ocean heat inflow may lead to thermodynamic recoupling between the ocean and the atmosphere and the amplification. So in other words, what we can see is it is a positive feedback. That means more thinning of ice leads to more melting of ice, which leads to more water, which leads to more absorption of solar energy, which leads to more heat, which leads to more thinning of ice. So everything is interrelated. That means whenever there is a thinning of ice, that results in increase in temperature. So here we are going to look at the next factor, which is the surface transition caused by the snow cover retreat. So here is an image which talks about the late spring snow cover is dwindling or reducing across the northern hemisphere. So here we see up to the year 1990 or close to the year 2000, we see many of the years the sea ice cover is actually increasing, but from 2000 onwards for many years we see the sea ice cover is retreating or reducing. So this is an image which exactly tells what is being observed over the period of several decades. The extent of hemispheric seasonal average snow cover increases in fall and winter, because that is the time the temperatures are low and the snow water starts freezing, but decreases in spring and summer. That means when the sun comes up, the ice starts melting. So the snow water equivalent determines the amount of heat needed to melt the snow, and it is important for the emergence of Arctic amplification. So this is one of the parameters which we can measure. From that we can identify how much is the temperature that is going to increase. The results of this snow water equivalent trends from the 36 years, that is close to 40 years passive microwave record, that is from 1980 to 2015. This suggests that hemispheric snow water equivalent is decreasing, but at the regional scale the trends are less certain and are highly variable. So if you see for the entire Arctic region, there is a difference happening, but if you look at very specifically at local trend, it is quite unpredictable. So that is what you can see from this image. So here we see the brown color spots are actually decrease in the ice cover. The blue color spots are increase in the ice cover. So if you see overall, what we can say is the ice cover is decreasing. That is the only thing we can say. But then there are certain places where it is white. White color means it is more or less remaining the same. And in few places it is dark brown. That means the ice is retreating. And in some other places the ice is actually increasing. So this is what overall we can say. In the Arctic, the ice is retreating, but regional wise, individual region wise, we cannot exactly say. Let us look at the next factor, which is the surface atmospheric coupling effect. So here, due to the shallow Arctic boundary layer, the obtained data from GPS radio accumulations is having low vertical resolution and accuracy. So this is again, even though we say satellite can help us understand the things, satellites take the picture from a very high area. So that means we may not even know what is the ground reality, or in the ground how much is there, because it mainly most of the time covers only the top of the layer. So top of the layer does not clearly tell vertically how much it is actually decreasing. So that amount we cannot easily find it out. But of course, recently more accurate measurements are being made to exactly find out even the thickness of the ice. So the temperature inversions in the Arctic are of radiative origin and could be unrelated to vertical mixing. That means even though water is the ice melts leads to water production and the water gets into the Arctic Ocean, but this leads to vertical mixing of waters. But this event is not very extremely an important event with respect to direct albedo effects. So unlike the open ocean, the turbulent fluxes in the Arctic region are influenced by the sea ice, frequent overcast cloudiness, high wind speeds, low winter temperature, and a small temperature contrast between the surface and cloud layers. So that's the reason these turbulent fluxes are not having a major impact on the decrease of ice. Moreover, these fluxes are greatly enhanced by the surface heterogeneity and the presence of sea ice sheets. So this is a very crucial factor. So that's the reason the surface atmospheric coupling effects are not having a major contributor to the Arctic amplification.